What I want to challenge you to do, the first step is, what we're going to introduce is what's called the second derivative test today. That's not going to mean anything to you. Everybody close your Chromebooks all the way, please. Put them all the way closed. So what I want you to, to do first, though, is I want us to make a connection between what the sign of the second derivative is and what the corresponding functional behavior is. Now let's start off by just thinking about first derivatives. If the first derivative is positive, what's that tell you about what's going on with the function there? It's increasing. Yeah, slope is positive. The ant's walking uphill from left to right, going in the positive x direction. If the first derivative is negative, the function is decreasing. So the ant's walking downhill as he walks in the positive x direction, right? So we want to be able to answer the same question for the second derivative, but it's not. The second derivative isn't quite as obvious. So let's go to Desmos and let's pull up. I'm going to do a new one. New blank graph. There we go. Okay. So let's take the function, how about f of x equals x cubed minus x squared minus 6x. Okay, let's take that function. There it is. Looks complicated. And let's take the derivative of that. So we're going to say g of x equals f prime of x. Okay, let's make sense of that. So where is it that the blue function is positive? Say it again. Negative infinity to, looks like negative 1.12. I mean, it's almost negative 1, right? So all the way from negative infinity up to that value right there, which corresponds with, look at that. The maximum is that, of course, has the same x value, doesn't it? Right? Because the ant's going to be walking uphill as he goes from negative infinity until he gets to the peak of that function, to the maximum, right? Everybody agree? Okay, and that's where he stops walking uphill, so the function stops increasing and it starts decreasing. So at that point, the value of the derivative swings negative for a while until he gets down to there, right? Now the ant's walked all the way down to the bottom of that valley, and that's where the function is going to transition from decreasing to increasing again. And of course, notice that the x values line up, right? Okay, question.
Why is there no special thing at the value of the blue functions corresponding with green?
Oh, okay, yeah. So, okay, good question. So the value of the blue function is there. If we evaluate the first function, let's do the point. How about 0.333, comma f of. Yeah, it's really doesn't seem to be anything too crazy, does it?
Isn't that the where it has the lowest slope?
No. But we'll come back to this. Does anybody see? Is there anything special about that point?
It's the middle. It bisects the distance between the relative maximum and minimum.
Okay, it does. It does. Now that's good eye. That's actually not crucial. In this case, it has that kind of symmetry, but it wouldn't necessarily have to. But there's something else about that point. Does anybody see something about that point? As we walk from left to right, something changes there. It's a hard one to see. This is not obvious at all. But it's what we're going to talk about today. Okay, let's come back to that.
Is it the amount?
We'll come back to the green point. I'm going to make it disappear for now. Let's do h of x is the second derivative of the red function and the derivative of the blue function. Well, that's just a line.
But it goes through that green dot we just quoted.
No, it doesn't.
It doesn't actually go through the green dot, but there's something significant about this. Now let me put the green dot back up. What do you notice? Oh, how about that? Look at that. The x-coordinates match up. That is not an accident. The 0 of the orange function corresponds to the x-coordinate of the green point. Okay. Now let's think about this for a second. Let's think about, I'm going to make the red function disappear. Think about the orange graph, which is the second derivative, relative to the blue graph, which is the first derivative, right? They have the same behavior as a first derivative would have to the original function, right? Somebody describe for me, why is the value of the orange function negative to the left of that point?
Because the slope is negative.
Okay, because the slope is decreasing, right? Because the blue function's decreasing, right? And the orange function has a positive value. I should probably be using my pointer here so you can. So to the right of this value, the orange, or to the right of this point, the orange value is positive because the corresponding point down here is a minimum and the function is increasing to the right of that. Okay, but now we got to step that relationship back by 1 because the blue function is in itself a derivative and the orange function is the derivative of a derivative. Okay, so think what this means. If the derivative is decreasing, the value of the derivative is decreasing, which is where the second derivative is negative, what's that going to look like? How would the value of, what's it mean if the value of the derivative is decreasing with x? Think about that in relation to the red graph. So for example, let's just pick a point and line it up vertically. Let's just take the point x equals, well, I'll just graph like x equals something and we can just change its value. So what if we do x equals -2? Okay, so at x equals -2, what do we get? At x equals -2 on the red graph, what's happening to the tangents as we move to the right? Okay, you know, that was kind of a cool thing to do. We just built a tangent. Yeah, that's kind of cool. Let's just do that real quick. Let's build a little tangent line so we can watch the tangent to the red curve actually change as we slide this thing, right?
Are you recording this?
I am recording this, yeah. So we can do this. We'll call this t of x for tangent. It's just going to be a line. What's the slope of the line going to be? What's the slope of the line going to be at x equals 2, for example? Right there.
F prime of -2.
Okay, it's going to be f prime of -2, isn't it? Right? Which is just g is f prime. So the slope, we're just going to write down the line mx plus b, right? Okay. Well, that's just going to be f prime. I'll write it that way so you guys can see it better. F prime of x, okay, times, that's the slope, times x. Well, you know what I need to probably do? Let's call this,
You can read some lines. Read lines.
I'm going to call that A. A times x okay, and then I got to do the line x equals A. Okay, that is going to work. That's perfect. Okay, so then plus, what's the y-intercept going to be? How are we going to get the y-intercept of this line? So we got this tangent line. How would we do that? If we've got this tangent to the curve that's going through, like, let's say the point right here. Right, so it's going to be doing this kind of thing. How do we know where it's going to cross the axis? So if the point of tangency is going to be at, we're calling it A, f of A, right? How do we know what it's going to be at the point 0, B? I can calculate a slope from this. I got 2 points, right? So what's the slope going to be? What's the change in x going to be? I got to do the change in y first, right? So like f of A minus b, whatever that is, right? Because we're going to go through the point up here at 0b, right? Divided by A minus 0, so just A, right? And what's m equal to? F prime of A, right? So the only thing I don't know there is B, right? Everything else I know. So I just got to solve for B. So what are the steps I would go through to solve for B? F of A minus B equals, if I cross multiply, A times F prime of A. I could add the B over here and subtract that away. And so I end up with B equals F of A minus A times F prime of A, right? Does that make sense? So that's what I have to add right there, isn't it? Right? Okay, and then I've got my equation of the tangent line. So hope this works. This should be pretty cool. A times F prime of A. Yeah, it worked. That's really cool. Huh. Check that out. So look what we got here then. Let me just make a bunch of this stuff disappear. So if let me make like this and this disappear for a second. And then does everybody see, let's change this color. How many colors we got? We'll make that one, I don't know, purple. Okay. So now, yeah, let's do that. So look what happens if I drag A then. See, look what that does. It gives me the tangent line. That's kind of cool, isn't it? Isn't that cool? Okay. So let's let A doesn't need to be that big either. Let's just let A go from -4 up to positive 3.5. Actually, we can go from -3. Then it won't be so sensitive in steps of, how about 0.2? See what it's doing? Oh, this is going to be great. Okay, so this will really help. So look at that tangent line then. If we put on, let's put these graphs back in. So now there's our derivative function, and there's our second derivative function, right? Everybody see that? So we were saying, turn this off for just a moment, we wanted to explore the behavior now. As the ant moves from left to right, what does it mean for the first derivative to be decreasing? So the rate of change, the slope of the first derivative is negative, right? The rate of change of the first derivative is negative. What does that mean in terms of a tangent? As the ant takes a step to the right, what has to happen to the value of the slope? It has to decrease. What does that mean in terms of the behavior of the tangent line? The tangent line is like giving us a visual representation of the slope. So what's the tangent going to do?
Start large, make it smaller.
Okay, it starts large and it gets smaller, for example, right? If we pick a value like a equals negative 2.4, that's a pretty steep tangent line, isn't it? The tangent is steep and positive, which makes sense because the value of the derivative there. Oh, I have to do that. Can't do that there, can I? I gotta put it below a. So down here, g of a is large. See, it's 16.8. It's big, right? But as I scoot to the right, let's scoot to the right by just 2/10. Look what it did. Now, what happened, you saw the tangent line switch. It got less steep. The value of the derivative went down. Okay? We can keep doing that. Right now, watch as it goes from left to right. Look at the tangent line. See what it did? Right? It's getting less steep, less steep, less steep. I skipped over 0. But at 0, it would have been flat, wouldn't it? Right, you get the idea? Okay? What does that mean about the shape, though? How would you describe that shape from the red graph? When going from left to right, the tangent is getting less steep. What does that tell you about what the ant's doing? I mean, what does it say about the shape, though?
Approaching 0.
It definitely did something. The tangent went from being steep to being 0. What does that tell us about the shape of this thing? As he's walking up,
Relative maximum.
it's going to be a relative maximum for one thing. But doesn't it also mean that, like, if the ant is standing on, think of it this way, if we put a tangent to the graph, if I drag that back to a place where the first derivative is decreasing, where is the graph relative to the tangent line? So if I go back to there, or there, would you agree that at this point of tangency, right, I don't know, right in there someplace, the tangent line is sitting on top of the curve? The curve is underneath the tangent line, right? Okay, another way of saying that is the curve is concave down. It's curving away from the tangent line, beneath the tangent line. And a way to kind of also think about this is, if rain were falling on the function vertically, the function would tend to shed the rain. It would just roll off the function, right? It's not going to pool up, okay? Where does the concavity change? Now let's watch the behavior of this, right? The tangent line is getting more negative. It's going from positive to negative. It's still getting more negative, isn't it? Now it's going from a small negative to a big negative. Somewhere in the middle there, though, it gets the most negative, and then it starts to get positive again. It starts to get more positive. There's 0. Now it's getting increasingly positive, right? Where did that happen?
That one green point.
At that green point, didn't it? Yeah, see, look right there. At the minimum of the first derivative, isn't that going to be the place where the function, the first derivative stops decreasing and transitions to increasing, right? Well, notice what that looks like in terms of our point. That's where it happens, isn't it? Right? Isn't that the point of transition of the concavity right there? Isn't that where the function goes from being bowl-shaped down, concave down, to concave up? Right? Points to the right of this, we're going to end up getting, like right here, notice that now the tangent line is below the curve, right? Instead of being on top of the curve like it was over here. Now the curve is deviating away from the tangent line above it, right? Over here, if a rain were falling on the function, it would tend to puddle up down here, wouldn't it? Because where it's in the concave the upward concavity. Over here, it's just gonna shed the water, right? To me, the best way to think about it, though, is the relationship to the tangent line. A function is concave down, where a tangent sits on top of the curve, and it's concave up, where a tangent sits below the curve. Okay, and this is the point of transition right there. Everybody see that? Okay, so what's that tell us in terms of the sign of the second derivative? Well, it's not an accident that the x-coordinates of those 2 points are the same. The 0 of the second derivative is the point of transition from negative concavity to positive concavity, right? To the left of that point, the function was concave down, which is a negative concavity, negative second derivative. Over here, it's positive second derivative is an upward concavity, or a positive concavity, right? So think about this parallel relationship. Critical numbers of the first derivative, like a place where the first derivative goes from negative to positive, is a transition in slope, right? And if it goes from negative to positive, that's a minimum, right? It's a transition from decreasing to increasing. If it goes from increasing to decreasing, that's another transition in the value, in the sign of the first derivative. That's a maximum. Okay, what are transitions in sign for the second derivative? Where the second derivative goes from negative to positive, what's that?
Concavity.
It's a concavity change, right? If it goes from positive to negative first derivative, it's also a concavity change. Well, we have a name for that special point, where the concavity changes. We call that an inflection point. Or a point of inflection, whatever you want to call it, same thing. Okay. Those are the places where we change concavity. Those are important. Concavity in a function is important. What if you're talking about, let's say you're looking at this from an economic perspective. If you're a quantitative economist and you're telling your company, okay, we got to be careful about how we're doing our pricing because, yes, we're profitable here, but we're concave down, right? Which means that even though as we increase, say, the price of our item, the profits are going up. The profit is going up at a decreasing rate, right? And so at some point, we're going to hit what's called the point of diminishing returns, which is based on where the concavity flips. And so this is the kind of stuff that real mathematicians would look at. That's another key point. Minima and maxima are obviously important, but so are points of inflection, okay? All right, so let's put this in another context then. So let me get rid of all this stuff. Maybe I should take a picture of that, huh? For the notes. Okay. Okay, let's get rid of everything. Okay, what's going on? Tell me the things that are special about this point right here.
Slope is 0.
Slope is 0. Okay. So we know that f prime of, if we call this value a, f prime of a equals 0, right? Okay. What about the second derivative? What can you tell me about the second derivative?
Moving 0 down.
It's negative because it's concave down. So then think about this now. If we add those two concepts together, if we have a horizontal tangent coupled with a negative concavity, what does that have to be? It has to be a maximum, right? Think about that. It has to be a maximum, right? Okay, and okay, does that make sense? What about down here? This is also a horizontal tangent, right? So if we call this value b, f prime of b equals 0, but the value, not the value, the sign of the second derivative there is positive, right? So I guess I should write this one. It's greater than 0. So what does that have to do? If I have a horizontal tangent coupled with a positive concavity, it must be a relative minimum. That's the second derivative test. Okay? Let's go through an example using our table. Oh, say it again. Is it too cold? Oh, is it? Okay, let me see if I can turn it off. Tell me if that helps. Okay, let me take a picture of that one too for the notes. Oh, it doesn't work, darn it.
Just like
Okay, so let's take an example. How about if we do let's just do this. Okay, so okay, so there's our function. First thing we should do is write down the domain. Are there any exclusions to the domain?
X cannot equal. Never mind.
Okay, Richard shook your head. How come there's nothing? You're right, Richard.
Because the bottom's always positive.
Bottom's always positive. Good, because x squared is non-negative, right? Okay, 0 or positive. And so domain's all reals. Okay, let's take a derivative. Now, pause here before you jump into this. Pause here, because I saw this a couple times on the test, rarely, but how do I want to differentiate that?
negative exponents.
Yeah, right. I do not want to use quotient rule, because the top is not a function. There's no need to use the quotient rule. That's way overkill, right? So we want to write this function as 6 times the quantity x squared plus 3 to the negative 1. Just use the chain rule, right? Okay, so what's the derivative going to be then? 6 is a constant. What's the derivative of hand to the minus 1?
Negative 1.
Okay, so that's going to be negative 6 when I multiply by the 6. Hand to the negative 2 times derivative of hand, which is 2x. Good. Okay. Okay, so then f prime equals, what am I going to get? Negative 12x over x squared plus 3 quantity squared. Or if I want to write it using a negative exponent, if I wanted to, I could write it as negative 12x times the quantity x squared plus 3 to the negative 2. Okay, let's say that in this case, I'm specifically asking you to find relative extrema and points of inflection, so we have to take a second derivative. Okay. If I were just asking for relative extrema, what we're going to see in this example is that trend I told you about. It's always the further you can work down the table, the easier things are. But if the second derivative is really hard to take, and all I'm looking for are relative extrema, don't bother. Just use the first derivative test, right? You only use the second derivative test when convenient, unless you have to find inflection points, and then you have to do it, okay? So, okay, so second derivative then. So we can go ahead and either use product rule here or quotient rule here. Let's just use quotient rule. How about? So what's that going to give us?
2 times
Hang on now. What is quotient rule?
lowers
low d high minus high d low. So here's my low times d high. Well, what's d high going to be? Negative 12. Good. Oh, you got it. Perfect.
In my car.
Oh, okay. Just bring it to me between periods.
Okay.
So minus high d low. So minus negative 12x times the derivative of the bottom. What's the derivative of the bottom? What's d low?
2 and 2.
Times all divided by bottom squared. So what's that going to be? Squared plus 3 to the 4th. Okay, so we got to do a little cleanup on that one, don't we? So then this is going to be, let's see, we could factor out an x squared plus 3 from the top. Everybody agree? And what are we left with? Negative 12 minus negative, so that's going to be plus, whoops, sorry, times, you got one of those left too, don't we? We factored out an x squared plus 3, so we have an x squared plus 3 left in that first term. Okay, now, what about up here then? So when we factor that out, that goes away, that becomes a 1. That goes away. So then we're left with minus a negative is plus 12x times 2 times 2x. So that's, what, 48? X squared all over x squared plus 3 to the 4th, but we could just cancel vertically there, right? And get, let's go ahead and expand that out. So we're going to get negative 12x squared plus 48x is 36x squared minus 36 over x squared plus 3 cubed, right? And then we can factor out a 36 on top. And so f prime of x equals 36 times x squared minus 1 over x squared plus 3 cubed, right? So that's a lot of work. Let's pull in our simplified versions of the derivatives onto a new page. So we have a little more room to work here. So we had, let's see, yeah, this guy. Okay, we had this guy right here. That guy. Okay, so now let's find our critical numbers, right? So where are our first derivative critical numbers going to be? And we're going to have to distinguish between first derivative and second derivative critical numbers now. First derivative critical numbers are the places where what could happen? Say, relative extrema, right? Relative mins and relative max, so peaks and valleys. Second derivative critical numbers must be the places where what could happen? Inflection points. Now, neither one of those is guaranteed to happen, right? We have to test for both of them. But you see that parallel relationship there, right? Critical numbers are just points of transition for their derivative, okay? So for the first derivative, what are we going to get? Are there any places where the first derivative is undefined? Yeah, because the bottom is always non-negative, is always positive value, right? But f prime of x equals 0 when what? when x equals 0, because that would make the top 0, right? We want to find the 0 of the numerator, tells us the zeros of the rational function. Okay, when x equals 0. So there's a first derivative critical number. What about second derivative? Second derivative is nowhere undefined, right? Where does it equal 0? 1 or negative 1. When x squared equals 1, so x equals plus or minus 1, okay? So now let's make our table. We're going to add another row though. Right now we've got x, we've got f, we've got f prime, and we've got f double prime. Okay, and our domain is all real numbers. Our only first derivative critical number is at 0, and that's a 0 of the first derivative, right? Okay, where are our second derivative critical numbers? Well, we said positive 1 and negative 1, right? Okay. Okay, so this is, and let's make a note of this. So this is a critical number, first derivative critical number. We'll just say it like that, how about? And these are second derivative critical numbers. Right? So what must be true of those? Zeros of second derivative. Okay? Okay, now, here's where this gets really good. Now, all the work we need to do, we can do in the third row, and it ends up being really efficient. So let's use the second derivative test here. We can use our first derivative critical number as a test point for the second derivative. What is, if we go up to this function right up here, what is f double prime of 0? And all I care about is the sign. It's going to be, if I plug 0 in, I'm going to get 36 times 0 minus 1.
Negative.
Negative, isn't it? We're going to end up getting negative on the top, positive on the bottom, which is negative. Okay, so what does that have to be? Think about this now. If it's a 0 first derivative, that means it's a horizontal tangent, right? If it's a negative second derivative, it means concave down, right? So it has to be like that. And this, I know this is kind of hokey, but where it's negative, where the second derivative is negative, the function is negative. It's sad, right? It's frowning. Where it's positive, it's happy and it's smiling, right? So it's just a quick way to think about it. Okay, so we know that that's going to be a relative maximum. What about these points right here? Okay. In order to know what those are, we would have to pick a couple other test points for the second derivative, right? Okay, so let's pick, like, you pick one out. What do you think?
Negative 2.
Okay, so if we pick negative 2, then what's the sign of this function at negative 2?
Positive.
It's going to be positive, isn't it, right? So we're positive right here. And then would you agree that at positive 2, this is an even function, isn't it? Positive 2, it's also going to be positive. So what is this point right here?
That's right.
No. Question, Josh? What is it? What is, so what's going on here? If the second derivative is going from positive to negative?
It's a relative maximum.
No. What do we call that? It's now, so think of this in terms of concavity. So here the function is concave up. What is it?
A bisecting middle point.
What do we call that?
Point of inflection.
Point of inflection. So it's going from concave up to concave down, which means there's a transition there, right? So that's an inflection point. So we'll just call this IP. Same thing here, right? We're transitioning from negative to positive. So it's an inflection point. What's that? Yeah,
Yeah.
yeah.
It's really
Yeah.
nice.
Okay, and so if we wanted to sketch this thing, well, we know what this is doing. This is, there's the x-axis, this was at 0, y equals 0, so there's the y-axis. Well, what's the value of the function at 0? If we plug 0 in, we're just getting 2, right?
Yes.
So at 0, 2, there's a maximum. At negative 1 and positive 1, what's the value of the function at positive or negative 1? Doesn't matter. 3 halves. Okay, so in both cases, we're just going to get 3 halves. And so what's this thing look like? So over 1, up 3 halves, back 1, up 3 halves. But we know what this thing has to do. It's going to go through where it's going to be relative max, but then the concavity's got to change there, so it's got to do something like that, right? It's got to change from concave up to concave down, concave up to concave down. Look at that. We got a pretty good sketch, right?
That's how we find out the end of the
Well, we'll do end behavior soon. That's coming up next. Yeah.
Is this
But we can add it to the table, yeah.